Merci. So hello, everyone. I will start the presentation. Hello, everyone. Thank you for joining this webinar with me, and thank you for the introduction. I'm pleased to present you today the results of my researches about anaerobic digestion. And let's start. I have divided this presentation into 4 parts. I will start with defining the notions that you have to know in order to understand the results. And then I will present you the first approach that we developed. And this approach consists of developing a database from literature. And then I will go to the second approach, which is the development of a strategy to optimize the inoculation that I will explain afterwards. And finally, I will give you the take-home messages. So let's start with defining what are anaerobic digesters. They are simply reservoirs that are enclosed. Inside of them, we put on organic matter, specifically found in organic waste, such as food waste, sewage sludge, etc., and manure. So what we do is that we want to biodegrade these wastes by specific microorganisms, and how we obtain them, we can find them in in many substances such as leachate, sewage sludge, etc. What we do is that we keep them in this digester under controlled conditions, and most importantly without oxygen, and this in the main objective of managing all of these quantities of organic waste that we are producing nowadays. So we obtain a valuable product, which is a biogas rich in methane that it could be used in producing electricity, heating, even cooking. I mean, some houses in China and in India, they are using methane. Like, normal people can do that, but I don't recommend you to do that at home. It's a little bit dangerous. We have a second sub product, which is a fertilizer that we call digestate, and we can use it. We can directly apply it on land, or we can further treat it by drying it or other treatments in order to make it more stable for the land. So if I want to, I have to give a second, a final note, which is that we can use the digestate also from another anaerobic digester as a source of microorganisms for new anaerobic digesters. I will come to this later in this presentation. So if I want to speak about the potentials of anaerobic digesters in numbers, I could say that we can reduce greenhouse gas emissions by 10% by 20 and 30 if we use anaerobic digestion. And if we gather all of the available organic waste that we have on planet and apply anaerobic digestion on them, we could produce mostly almost 20%. We could cover 20% of world electricity consumption and 5 to 7% of inorganic fertilizer use. But why we are not taking advantage of those potentials? Mainly because of 2 reasons. The first one is legislations. There are lacking of legislations in some parts of the world and some governments, such as for example, Africa, to encourage and push municipalities, industrials, and even agricultures to apply anaerobic digestion on their organic waste. And this is something that we researchers don't have a big ability to participate in. But the second hurdle to the application of anaerobic digester globally is the lack of knowledge about its optimization, technological optimization, and operational optimization. And that's when where we wanted to get involved. And specifically through optimizing what we call a startup phase. So what is a startup phase? It's simply a duration of time that constitutes the age of an anaerobic digester. So through which we want to establish active bacteria. So at the beginning, we will have like small amount of bacteria that can biodegrade our organic waste. And we want to adapt them to specific design parameters of our process. For example, if we target to biodegrade our waste under 50 degrees Celsius, so we will be increasing the temperature progressively in order to attain the value that we want. Once this phase has been achieved, we arrive to a stability, more or less stability phase, or what we call a steady state phase, that will continue with us for the rest of the age of the anaerobic digester. If there are no important changes in the biogas facility, for example, if they haven't changed their engines, or if they didn't add other flows of organic waste. So during the steady state phase, there is stability of anaerobic digestion parameters. As I said, for example, if we target a temperature of 50, then during the steady state phase, we have temperature of 50, we don't change it. So when we know that our startup phase have been achieved or have been finished, we have just to look to our graph or methane. So when we find that the methane production and mostly other parameters like pH and acids production, when we find that when the methane, specifically the methane is more or less higher than the other days and starts to be more or less stable, then we achieve the steady state phase. So now, why we want to optimize the startup phase? We want to optimize it because it's a phase that it's characterized by instabilities. As I said, operation parameters are changing, methane and biogas production are not stable. So for that reason, we could encounter serious risks of microorganisms growth inhibition, and that's something we don't want to have in our facility, because we want them to proliferate a lot so they can biodegrade our organic waste in a bigger rate. So in order to avoid that, what we do is that we avoid feeding or bringing organic waste into our anaerobic digester. And this will lead to the accumulation of waste with all of the environmental and economical problems. So this means that we will have economical losses because our facility is running, we have engines running, and we have low income. So we are not producing anything. So this is not optimal for our biogas facility. And for that reason, we want to our main target is to reduce the startup duration. So all of our approaches will be around this, which is the reduction of startup duration. And here I want to note that decisions during the startup phase could mean more or less thousands, if not millions of dollars saved or waste. So every decision is important. Now, let's move to the objectives of this research. So mainly we wanted to develop knowledge-based approaches because mostly with regards to the startup phase, what has been done in literature is that, or even in experimentation, so people do an experiment with specific conditions, with a specific under specific temperature, with a specific type of waste. They get their results and they say, okay, this is achievable in this time, and it happened in a good way. And other people they try other conditions, but there is no standard guidelines, if you want, regarding the startup phase. So if I have a new conditions, what do I do? So at first we want, as all researchers, I think, we went to the literature and we developed a database, and then we tried to validate it in order to use it as a decision support tool for researchers and even for operators of anaerobic digesters. Then we wanted to develop an approach for the optimization of the inoculation strategy, and I will explain that further in this presentation. So let's start with the first approach. So as I said, we went to the literature, and instead of doing a classical literature review, what we did is that we gathered all of the numerical and even categorical variables, and then we put them together in a matrix, of 75 cases, which are the rows of this matrix, and 16 variables, which are the columns. So what we did is that we did a selection of data. We calculated the missing values if enough information are available. We standardized all the units, and we obtained this matrix. So basically, if someone wants to have an idea about the conditions, for example, that are close to his or she's a condition. So what you do is to go and look, for example, for the temperature, and then the type of feed and the type of inoculum, and then you see how they increase their rate of feeding, and then you check their results and compare with your results. So there could be a good tool for or a reference for researchers and even operators of biogas facilities for comparison purposes. But we wanted to take it to another level. We wanted to know, can we validate this database, all of this data coming from other people's studies, and can we capture the links or correlations between variables, because we have now a source of compacted information. So the answer is yes, we can do that. And we tried different methods, but what we found interesting was with the PCA, which is the principal component analysis. So it's, well, briefly, it's a type of, it's a method that makes you able to get rid of redundancies in your matrix and compact or gather your variability sources, and then project your data points in a other axis. So for example, if we have two variables, we have two axes, but here I have 16. So what to do? I cannot show my data points in 16 axes. So that's why we applied PCA. Then we wanted to know if there are some groups of startup studies, and here we represented our data or startup studies with yellow circles. So small yellow circles means short startup phases, and big yellow circles means extended or long periods of duration of startup phase. So then we looked to each group, and we wanted to determine if it could be characterized from the two others or not. So the first one with small circles, we found that it has that it's characterized by relatively high feeding rate, and this led to a low startup duration. And we concluded that high organic loading rate, which is the rate that we use to feed or to introduce organic waste into the reactor or the digester, is something that could improve the biogas production and microbial activity, of course, to a specific extent. We cannot increase it to the infinity. And this was also found in literature by other researchers. And the second group was a mixture of short and long startup durations. So when we looked to their characteristics, we found that they have moderate startup durations, and they were characterized by low organic content of feed. So when we look to their substrates or to their organic waste they are processing, we found that they dilute it, and we conclude that this is not optimal for the startup phase. And for the third one, it was the startup cases were specifically characterized by mesophilic temperature, which is between 35 and 38, and they had a low feeding rate. And also we concluded that those conditions should be avoided during the startup phase. Now that we have a qualitative idea about some conditions that we have to prioritize over others, we wanted to have a quantitative idea about the impact of our variables on the startup duration. So what we did is that we performed a random forest regression model. It's a bench, it's a code or a method to develop many models. In our case, we developed 300. And then when you say regression, you have to choose a response or dependent variable. So here we choose the startup duration as our dependent variable, and the other variables are our independent ones. So what we did is that we didn't aim the prediction of the startup duration, because the anaerobic digestion process is complicated, and we cannot do that. And startup duration is a period of time. You cannot predict a period of time using regression, but instead what we wanted to do is that to use the structure of the model in order to understand the impact of each variable on the startup duration. So for that purpose, we measured or calculated three variable importance measures, which are the mean minimal death and mean square error increase and node purity increase. So if I want to conclude what those things do, so basically we calibrate a model with all of the variables, and then we go variable by variable. We subtract this variable, and we calibrate the model again, and then we calculate the error. If the error increases, then this variable is important to the model. If the error decreases or stays constant, this variable is not important. And then we gave a score to each variable, and we classified them according to their impact on the startup duration. So what we found is that these five have more or less the biggest impact on the startup duration. And what unites, or what could have make them link together is the feed dilution. So when you, as we saw in the PCA, or the principal component analysis, so this validates what we found previously. So when you dilute your feed, you increase your hydraulic retention time, which is the time that an organic waste stays inside the reactor. So the more it stays, the more it will take time, and the more your startup will be the longest the startup is. Another important note was that the weak impact of reactor scale. So what's that supposed to mean? It means that when you have results from lab scale reactors and full scale reactors, you can compare between them both. Or when you have results from lab scale reactors and you want to study what would happen if you have a full scale one, it could represent what's happening in terms of startup duration. So now let's move to the inoculation strategy. The inoculation strategy is a lot of decisions that we make in order to bring microorganisms inside the digester. It's also called seeding. So at the beginning of the presentation, I said that we can use digestate coming from another anaerobic digester to start up as an inoculum, to start up a new digester. So saying that, let's say that you want to do that, and you are designing or you are preparing a protocol for the startup of a biogas facility. So first thing, you have to check the source of your digestates. Well, you localize them, and then you check. You have to ask three questions. Basically, what are the organic waste they are processing, under which temperature, and is it stable or not? If no, you have to change your source. If yes, we have to pick one of these sources. And what we want is that we want a source of microorganisms that ensures a rapid startup. So for that reason, we performed experiment, test runs, BMP tests. So it's a test, biomethane potential test. It's a type of test that are intended to determine the maximal potential or maximal methane production that an organic waste can produce. So it's intended to assess the organic waste, or what we call a substrate, and not the inoculum itself. But we wanted to see if we can use it to assess an inoculum. So if we see a difference, then it's a good way. So this test is run in a standardized way. We performed that in triplicates. We had the triplicates of blanks with only inoculum. So this represents our noise of data, and we have triplicates of positive control. So positive control is a substrate or organic matter that we know its theoretical potential of methane production. So here we used cellulose, microcrystalline cellulose, and then we had triplicates of our sludge. of our substrate, which is sewage sludge, and we used the same sample for our 3 test runs for our 3 inocula. We did that for 30 days for each test under 55 degrees Celsius. So the first product of this experiment was the biomethane potential of the sewage sludge. So we checked them, we see some differences, but when we applied ANOVA, it's not significant. And then we checked something else, which is the cumulative specific methane production of our sewage sludge. So when you look here at the end, you arrive at the, like 3 inocula, they arrive at almost the same value, but at the beginning you can see that there's a delay here for inoculum 3. So that's why we applied a model, first order exponential model, and we wanted to, to compare between the 3 inocula, we calculated the K, which is the kinetic constant. So we found that inoculum 2 had a better kinetic constant, and inoculum 3 had the least good one. And when we check why, we check their characteristics, we found that inoculum 3 had more ammonia than these two, and inoculum 2 had less, the least ammonia and volatile fatty acids concentration. And this was found before by, well, validated before by other researcher. So then we wanted to explain why inoculum 2 is better and why inoculum 3 is not performing well in terms of kinetics. We checked the composition or the structure of their microbes. So here you see the relative abundance of the phyla that we found in our 3 inoculum samples. At first, we compared between the 3 inocula in 2 levels. The first level is the relative abundance. So in each one, which one is dominant. So in inoculum 3, if you remember, was the least rapid one. It was dominant by Firmicute and Bacteriodota. And when we looked to their characteristics, we found that they are protein degrading microflora. So when you degrade protein, you obtain ammonia. You increase ammonia in your inoculum, and this is not good for our kinetics. Inoculum 1 was mostly dominant by proteobacteria. It had also good results, but a little bit less than inoculum 2 in terms of kinetics. So we found that this could be because they have 40% of proteobacteria, which are producers of hydrogen and CO, and these two components are afterwards consumed by other bacteria to produce methane. And then we compare between the 3 inocula in terms of absence and presence of some taxa or phyla. So we found that here in the blue color, there was Actinobacteriota in inoculum 2, and those are bacteria that secrete enzymes for the metabolism of organic matter. So they make the process more rapid. And we found that there are Desulfobacteriota that are thermophilic bacteria, centrophic, which means they produce things for other bacteria, for methane-producing bacteria specifically, and other phyla, they are responsible of decomposition of simple sugars, and this will accelerate the process. So this could explain why inoculum 2 was better. Then after selecting our champion, let's say the best inoculum, we wanted to know if we sample our inoculum from the directly from the anaerobic digester or from a post-treatment reservoir. Let's say that in one of the biogas facilities, there's a reservoir or what we call a post-treatment reactor. So for that reason, we compared between freshly sampled inoculum or digestate and post-treated one. And for that, we used a semi-continuous experiment of 2 reactors with 5 liters each, using sewage sludge as substrate under 55 degrees Celsius for 114 days. So what we found is that, as you can see, the pink circles that represent the fresh digestate or the fresh inoculum, they outperformed the green one almost along the whole experiment, but most significant differences were found in weeks 4 and 7 just after we increased our organic loading rate in an important way. So we concluded that the fresh inoculum or fresh digestate is more adapted to fast organic loading increase. So if you want to apply the strategy in your new digester, you have to find or to sample a fresh one and not a post-treated one. Then we had another question, which is, okay, digestate is good, we all know, because it has a lot of microorganisms at the beginning of the startup phase, but we know also that sewage sludge had some microorganisms. So what if we use the sewage sludge as inoculum, and we wanted to compare between it and between a startup with digestate? And for that reason, we ran a third experiment. So we used a system of 2 reactors using a mixture of sewage sludge and municipal organic waste under 55 degrees Celsius for 35 days. So here, pink circles, reactor 3 that was inoculated with digestate. And even though it was started up after 2 weeks of reactor 4 that was inoculated with sewage sludge, there was a better production of biogas, and we wanted to quantify this production. I just want to note here that we know that digestate is better than sewage sludge. We wanted to compare between both of them because digestate is we have to buy it. It has a cost, and sewage sludge is free. So we wanted to know how much we gain money if we use digestate. So here we had like 10 more times biogas produced in reactor 3 and 1.5 more waste was processed in reactor 3 and in shorter time. So we wanted to translate this in costs in order to select our inoculum. So 11 more time money, sorry. So we paid more money, 11 more money in reactor 4, and we paid 3 more times money in reactor 4 to process 1 kilogram of organic matter. So now we arrived to the conclusion. So through this research, we wanted mostly to develop approaches for the optimization of the startup phase, because there is a lack of those approaches, and because mainly the information and literature is scattered, sometimes also contradictory and non-conclusive. So first thing we did is that we developed a database, and then we assume it's a reliable tool for comparison purposes. We applied machine learning on it, and we proved that machine learning could capture some of the complexity of anaerobic digestion processes. So this method could be used also on other, well, it has been also used on other, for other purposes, such as the development of databases to understand the nitrogen and digestate. And then we use the biomethane potential tests that are, as I said, intended for the characterization of substrates and not inocula. So we use them, and we proved that they could be used to characterize the inocula if you use kinetic analysis with them. Then we proved that fresh inocula are better for full-scale digesters if you are willing to use the or apply an approach of a rapid startup phase, or what we call an aggressive startup phase. And then we proved that digestate is better than sewage sludge in terms of production and costs. And so economical analysis have been a good tool to choose also the inoculum. Thank you so much.